guys. Hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at a second bit of the concept of a translation partition function. And this is going to be a follow-up video from the first one, which we had looked at the concept of a translation partition function considering a monoatomic ideal gas. Now, in our last discussion, we had said that basically we can represent the translation partition function of a monoatomic ideal gas. And considering that this gas is confined within a cubed box, whereby we say that this is going to be the summation of nx and the exponent of negative nx squared h squared. And this one was given as 8 pi squared, and then we had L. And of course, so this is not the case. This is going to be 8 ml squared, and then we had kbt, which gave us the particular equation for representing the partition function of this specific monoatomic ideal gas in a particle in a cube. And of course, we had said that we can be able to perform an approximation to this one in order to find a standard way of representing this specific, or find a way of representing this specific equation in a sense that the standard integral can be used. Now, in this case, we are going to consider the translation energy levels of this particular integer quantum numbers of nx to be so close, and therefore that's going to allow us to perform an integration instead of a summation which has been given as such. So we're going to consider values of these specific quantum numbers ranging from 0 to infinity, and therefore we're going to have this equation given in a fashion of the translation partition function is equivalent to the integral between 0 and infinity, and this is going to be the summation of nx, the exponent of negative nx squared h squared all over 8 ml squared kdt. And this, of course, was in consideration to these specific values for dnx, which I've set for this particular representation. Now, in this case, we are going to look at a way of finding this specific the solution to this specific equation. And of course, we are going to solve this one using a standard integral, and therefore that's going to give us the value of the translation partition function equivalent to the values of 2 pi mkbt all over h squared, and that one is given as 3 over 2 v. Now, in this case, the concept of a v, which of course has been obtained from this particular case due to the product of the integral. Remember, we had said that we're going to consider a one-dimension box which gave us a solution to Schrodinger's equation for giving us the allowed energies, which had a dimension of L. Now, in case we consider a cube, which we had first given in this particular order, considering this specific 3 quantum numbers to be the same. Therefore, that's going to give us the concept of L cubed, which is going to give us the volume. And therefore, that explains the reason as to why we're going to obtain this particular aspect of volume. Now, in this case, we're going to reduce this particular equation by using the concept of the de Broglie wavelength, which is given in terms of the de Broglie wavelength, or the thermo de Broglie wavelength, given in terms of the ratio between the square of Planck's constant and 2 pi mk bt given as such, and this all of these values going to be given as a root or a square root given as such. So therefore, if we would try to consider the de Broglie, the thermo de Broglie wavelength, we're going to do a substitution into this specific equation. In that, it's going to give us the product of the translation partition function given in terms of this specific value of the negative cube root of that specific value for the de Broglie wavelength times the volume given as such. So if you try to look at this specific exponent together with that one, that's going to give us a product of 3. But since we can see that these specific values have been given in terms of reciprocal, then therefore this is going to be a negative value. Therefore, we're going to obtain a negative value of the de Broglie wavelength of the exponent of 3, or 1 over lambda to power 3 times the volume. And this is going to represent the translation partition function of a monoatomic class, considering those various factors, especially of the equal number of the quantum numbers, integer quantum numbers of n. And then we're going to see that if we consider this specific aspect of the de Broglie's thermal de Broglie's wavelength, then we're going to end up with this specific representation for the translation partition function using that approximation procedure. In this case, this is going to form our last bit of the concept of a translation partition function. And in some of the areas whereby we are going to involve the concept of application, of course, I'm going to be quoting this specific discussion. So that is it for now, guys. Bye, God bless you. Catch us in our next video.